In this presentation, I'm going to talk about how to improve rowing performance and, specifically, how technique choices you make can affect rowing performance. I'm not going to talk much about the physiology of training because that's well known. In fact, I would bet that what I'm going to talk about will be brand new information to most of you. The technique decisions you make can reduce the performance potential of those muscles you've already spent a lot of time training. This is about getting the most bang for your training time buck. Even the best rowers have probably not considered some of what I will present and could be missing out on perhaps 5 to 10% power improvements through simple changes that I will present. The presentation will be somewhat tedious for many of you, but I need to give the background that has led me to this point, so you're not left wondering, where did this come from? Much of this comes from after many years of analyzing cycling power generation, so there will be times you will probably wonder why I'm talking about cycling. I will be talking about cycling to help you understand the principle that I am now applying to rowing. Rowing is primarily an aerobic sport. That means your ability depends mostly upon how much oxygen you can get to the muscles. That's why you train. As everyone knows, you can improve rowing power by training to improve your aerobic and athletic ability. The harder you train, the better you are, unless you get injured, of course. Many think that's all there is to it. Nothing could be further from the truth. So you train hard to improve your ability, but beyond training, there are 3 separate technique considerations that can hurt your performance by reducing muscle efficiency and/or oxygen delivery to the muscles. When you hear these issues, I think you will agree that these have been generally ignored by the rowing community. Before I get to these considerations, who am I? Why am I qualified to talk about this stuff? I'm Dr. Frank Day. I rowed crew at the U.S. Naval Academy back when shells were still made of real wood, graduating in 1966. Our head coach, Paul Quinn, was always trying to bring science to the water, even once experimenting with non-Newtonian fluids in an attempt to reduce shell drag to increase shell speed. Last year, he had done an engineering analysis of how technique could affect shell speed variation and, hence, average drag. He then completely changed our recovery and catch technique to put his analysis into practice. We went from being a fast at the release and slow at the catch, what pretty much everyone did back then, to slow at the release and then constantly accelerating up to the catch. It seemed to have worked, as that year Navy swept the IRAs. After graduation, I became a nuclear submariner. I continued rowing and even coached a women's college crew for 1 season while in school. After 5 years in submarines, I went to medical school. In medical school, I had mentors who taught marathon running to heart attack victims, so I learned long-distance running. Eventually becoming an ultramarathoner, my 2 most noteworthy runs being 72 miles around Lake Tahoe and 37 miles from sea level to over 10,000 feet up Mount Haleakala in Hawaii. In 1978, I diversified a bit and participated in the very first Ironman race, a 2.4-mile ocean swim, 112-mile bike ride, and 26-mile marathon combined, finishing 8th of 12 in just under 17 hours. So you can see my athletic and educational background is pretty diversified. I believe it is this combination of medical, engineering, and athletic experience that few have that has helped me to see data differently and draw conclusions I am presenting here. About 25 years ago, after reading an article in Scientific American about the human-powered vehicle land speed record, I got to thinking about putting what I thought was the more powerful rowing motion into an aerodynamic container and perhaps exceed 100 miles per hour. My exploring this caused me to stumble across a new training tool that seemed to dramatically increase power in cyclists. I abandoned my HPV ideas to pursue this project. I called this device power cranks. Before I move on, you should understand what power cranks are because my power cranks experience is important to my having developed this understanding of physiology, which I'm now applying to rowing. Power cranks are independent bicycle cranks. I simply placed a one-way clutch in each crank arm. Both cranks will drive the bicycle, but one crank will not turn the other. In order to use power cranks, the rider has to be attached to the pedal to lift the pedal up to the top before they could do the downstroke push. Each leg can weigh about 30 pounds. On regular cranks, the other crank helps push that recovery leg to the top because most cyclists just partially unweight on the upstroke. Power cranks doesn't allow that help. Just lifting the leg doesn't sound particularly hard until you realize that the cyclist has to lift that 30 pounds about 14 inches to get to the top, and to do so about 90 times a minute for hours on end. That is not easy without help. As you can see from the video, the power cranks are different than any bicycle crank you've ever seen, not only training the lifting muscles, but training a better pedaling coordination. Power cranks did two things for the cyclist. It gave immediate feedback when one wasn't using the entire circle, and it made it possible to get enough repetitions to actually train the muscles and coordination to be able to do this for a 5-hour race. It's not possible to change ingrained technique without both feedback and many repetitions. Power cranks made it possible, and many experienced competitive cyclists saw a 40% power increase when they did so. Before seeing increases in power, though, new power cranks users usually saw reduced power because the undertrained muscles simply couldn't keep up. The weakest link is always the limiter to performance. This is why it's more important to train your weaknesses than your strengths. It wasn't until after 6 to 9 months of immersion training that new users typically reach the 40% power increase mentioned. Such changes are not magic, but require hard work over a long time as the necessary physiological adaptations occur slowly. A 40% power improvement in trained cyclists in one season is such a huge power increase, it was difficult to explain, as simply completely unweighting can only account for about a 10% gain. But the increases were real, so how to explain it? This presentation is the culmination of what I learned in understanding the 40% power increase cyclists saw when they trained on power cranks and applying that knowledge to rowing. Almost all of it can be explained through inefficiencies associated with muscle physiology, with a smaller portion related to dynamic losses. So we will be taking a deep dive into muscle physiology where most of the explanation lies. But before that, let's look at the big picture for a second. As I mentioned earlier, there are 3 ways any athlete can improve power beyond training. What are those 3 ways? 1, athletes can improve the efficiency of the engine they've already trained. 2, if fuel delivery is a limiter, athletes can improve fuel delivery to the muscles. Fuel delivery is the limiter at the anaerobic threshold. And 3, athletes can train a better balanced and possibly a bigger engine. Improving efficiency means using the already trained muscles more efficiently, that is, getting more power per oxygen molecule consumed. Improving fuel delivery means raising the anaerobic threshold. And getting a better balanced and bigger engine means using more slow twitch muscle fibers to avoid using the less efficient fast twitch fibers to generate power and, again, increase anaerobic threshold. All 3 of these can apply to rowing. How to do these things? That's pretty much what this talk is about. Pay attention. It took me a long time to gain my current understanding. I'm going to try to give most of it to you in about 30 minutes. Exactly what do we mean by power or efficiency in sport? When you see 200 watts on the meter, what does that mean? Power is simply how much useful work the muscles perform in an increment of time. Let's assume, for the purpose of this talk, cyclists and rowers both perform at an approximate 20% muscle efficiency level. What does this mean? It means that when you see 200 watts on the power meter, your muscles are burning 1,000 watts of energy. Only 20% of the energy burned ends up doing any useful work. If you want to improve just 20 watts, you need to burn 100 watts more energy. But another way to increase that 20 watts would be to reduce losses to improve the efficiency 10% from 20% to 22%. That improvement can occur without changing the current muscle capability at all if you can do it. Which way is easier? Well, it depends on how easy it is to improve efficiency. Let's look into that. Improving efficiency is where the easy improvements are found for most in both cycling and rowing. Improving efficiency means reducing losses. Losses are everywhere. Friction is a common one everyone is familiar with. In rowing and cycling, the easiest one to address is inherent muscle losses combined with some kinetic losses. Let's look at that. Muscles can contract at a maximum efficiency of about 40%. So that is the theoretical maximum anyone could achieve. An impossible task, as there will always be some friction and kinetic losses. But 20% means half the potential of the muscles is lost before useful work is done. That means there must be a lot of losses getting us to that 20% number. Can we reduce any of these losses? Of course, the answer is yes, or I wouldn't bring it up. Let's look first at that 40% number. That 40% maximum muscle efficiency occurs only at one muscle contraction rate for any given power. If the muscle is contracting faster or slower than that optimum, the starting muscle efficiency will be lowered. Power equals force times speed. Many think that if the speed is faster, then less force is required to get any power, so faster must be easier. But contracting a muscle fast costs the muscle a lot of energy, reducing efficiency. While the external force may be less, contracting too fast is actually harder from a muscle energy perspective. Contracting too slow is also inefficient because it requires higher force, which means using more, less efficient, fast twitch fibers. There is an optimum, most efficient muscle contraction rate for any power. Most cyclists and rowers ignore this issue. If the first step in the power transmission cascade is not performing optimally, nothing downstream can fix that, and your starting potential is lowered. It is this inefficiency that is easily reduced in most rowers and cyclists. So, how to do this? Let's look at a cycling example. In cycling, muscle contraction speed is controlled by pedal speed. Pedal speed at any power is controlled by the gears chosen. Gear selection on the bike is like changing drag factor on the ergometer. Most of us do not have the capability to actually measure oxygen consumption, but one can test for efficiency looking how heart rate changes with different pedal speeds at any given power, because at aerobic efforts, heart rate changes with oxygen consumption. Here's an example of how to test for this. This is a national champion age group triathlete testing for pedal speed efficiency. All data was gathered at 200 watts near his racing power. The y-axis shows what I called pulse power. That is power divided by heart rate, watts per heartbeat, so higher is better. We can see that his maximum efficiency at this power is at about a pedal speed of about 1.1 to 1.2 meters per second. He used to race at a pedal speed of about 1.9 meters per second. Simply finding him a more efficient pedal speed gave him an approximate 20 watt or 10% power increase. In this elite athlete, this relatively simple test resulted in a 10% increase in power at his racing efforts. How to do this in rowing? The principle is exactly the same. In cycling, pedal speed determines muscle contraction speed. In rowing, slide speed determines muscle contraction speed, and if one keeps power constant, drag factor determines slide speed. I ran a little test, and at 100 watts and 20 strokes per minute, slide speed changed from 1.75 meters per second to 1.25 meters per second, going from the easiest to the hardest setting. Again, it's a fairly simple thing to do to test for optimum contraction speed, at least within this range. Simply do multiple trials on the rowing ergometer, keeping power, stroke rate, and stroke length constant, then changing the drag factor and see how it affects heart rate. It is hard to keep power constant on a rowing ergometer. A bicycle ergometer will do it for you, but it is important to the analysis. Heart rate is a proxy for oxygen consumption varying approximately with the square of the heart rate, so a couple of beats is significant. Lower being better. Once the best slide speed is determined on the ergometer, this can be transferred to the water using a video analysis to compare slide speed in the shell to that of the ergometer, assuming power to be about the same. Drag factor on the water is changed by adjusting the fulcrum point on the oar being nothing more than a lever. A shorter oar handle will give a higher drag factor and slower slide speed for the same power. A secondary benefit of a slower dry speed is this also reduces some of the kinetic losses associated with accelerating the body back and forth. Reducing these kinetic losses will also improve efficiency, although this improvement has nothing to do with the muscle physiology. Most will find efficiency improved if drag factor is increased to slow muscle contraction speed. In fact, I can say pretty confidently that many will see about a 10% increase in power, just like our cyclists. Why am I comfortable in making this prediction? Because this benefit has been shown scientifically. Kane shown the drag factor to be effective in improving efficiency in rowers, seeing an approximate 10% increase in efficiency between a drag factor of 100 and 150. Again, drag factor affects both muscle efficiency and kinetic losses in rowing. My problem with Kane's study is he only looked at 2 drag factors. While he showed drag factor affects efficiency, one cannot know what the best drag factor is until tested to the point of going too far. Testing only 2 points can determine which of those 2 is better, but one cannot know if the better one is also optimal. Let's move on to the second physiological factor I mentioned that affects power, fuel delivery. In rowing and all athletics, fuel delivery means delivering oxygen and carbohydrates to the muscles. In aerobic sports, this is one of the main purposes of training, increasing capillary density and the ability of the heart. But the last step in the process, getting oxygen to the mitochondria in each muscle fiber, is affected by technique. Here is the problem. When a muscle contracts with force, it squeezes all the blood out of it. There is no blood or oxygen in the blood vessels that can replenish the muscle work being done when the muscle is contracting vigorously. This is what is responsible for the venous pumping effect of exercise, enhancing blood flow back to the heart you've probably heard about. But while enhancing cardiac output, this isn't all good. At the end of each contraction, there is a further delay while blood enters the muscle, gets to the capillaries, then oxygen diffuses to the mitochondria before any energy replenishment occurs. No oxygen is delivered to where it needs to be while the muscle is contracted and for a short period after. Now we can look at how technique affects fuel delivery. let's assume the power contraction lasts 0.9 seconds and the other delays 1/10 of a second. At 20 strokes per minute, oxygen is not being delivered to the muscle 33% of the time, or 20 seconds of every minute. At 30 strokes per minute, 50% of the time, and at 40 strokes per minute, 2/3 of the time there is no oxygen being delivered. Repetition rate has a huge effect on when athletes go anaerobic and how long they can sustain being anaerobic. Even though one may have to apply more force for the same power at a lower stroke rate, the fact that there is more time for oxygen delivery to the mitochondria to occur can more than make up for this. A high stroke reduces efficiency even more than this. If stroke length stays the same, kinetic losses from accelerating the body back and forth will increase with a cube of the stroke rate. While this, again, has nothing to do with muscle physiology, it is something else to be concerned about. Increase your stroke rate and energy losses increase big time, just as oxygen availability decreases big time. Finding out the sweet point for stroke rate requires doing the same type of testing one needs to do to find the best slide speed. Remember, I initially said there are 3 ways to increase power in an engine. I've talked about improving efficiency and oxygen delivery issues, but getting a better balanced engine is another. A better balanced engine can also lead to a bigger engine. Is there a way to get a bigger, better balanced engine for rowing? Remember, all of the power comes from the muscles. A bigger, better balanced engine means using more muscles, but differently. How can rowers do this? Again, let's look at how cyclists do it. Cyclists are better balanced and can use more muscles because they can both push and pull when generating power. Check out this representation of muscle work done when a typical cyclist generates 250 watts power around the pedaling circle. 250 watts is what a good amateur can maintain for 5 hours, 125 watts generated by each leg. Most of the work is done by the anti-gravity muscles pushing down, with a smaller contribution by the flexors on the backstroke. An even smaller contribution is seen across the bottom, and the smallest contribution over the top. Is this ideal? No. This is just what everyone learns because everyone learns on platform pedals, so they cannot do more on the upstroke or over the top, or they would come off of the pedal and not be ready for the downstroke. They learn to partially unweight, just getting ready to push down. When they get older and get attached to the pedals, when they could pull up, this pattern has become ingrained and is almost impossible to change, and most don't, except for brief periods when they are thinking about it. The cyclist has the potential to do more, but usually doesn't. The problem many don't realize is the power seen on the power meter is the average done around the entire circle. So we see most of the power is generated in only about 30% of the circle. To average 125 watts here, what he will see on his power meter, shown in yellow, this cyclist has to generate a peak of over 300 watts. This is a lot like rowing, except the rower cannot contribute anything during recovery, so a rower must push even harder to do the same amount of work. This is shown in orange, where, using the same pattern, the peak is now about 385 watts to average that 125. If you think just pushing harder is the best way to increase power, you will only get about 1 watt on the power meter for every 3 you push harder. Not very effective, in my opinion. The green line here shows the muscle contribution of a power cranks trained pro triathlete at the same wattage. This is about as balanced as one can get and what is meant by the term pedaling in circles. To average 125 watts, his peak is about 135. By using more muscle on the backstroke and across the top and the bottom, it's possible to use less muscle on the downstroke to generate the the same overall power, since overall power is the average of what one does during the entire cycle, not the peak seen during the cycle. It is possible to balance the power generation between all the available muscles, at least on the bike, where the only muscles used are the leg muscles, and they have pretty equal abilities. The typical pattern, while giving the same power and using about the same amount of muscle fibers, is less efficient because those peaks usually require utilizing the less efficient fast-twitch muscle fibers to achieve those forces. Balancing the muscle use allows using fewer fast-twitch fibers. What if these two cyclists want to increase their power 20%? Let's look. The red line shows a 20% increase in power in the balanced cyclist, which is likely to occur without ever invoking much fast-twitch use. Whereas the purple line shows what needs to be done if one is to increase 20% using only half of the stroke. Everything must increase 40% to see a 20% average increase if one is using half the stroke. Balanced muscle use should be more efficient than unbalanced muscle use for this application. Of course, cycling is not rowing. I hear the questions now. It's not possible to use the other half of the leg or arm muscles to generate power when the oar is out of the water. Or is it? Of course it's possible, or I wouldn't be bringing this up. How can the rower store potential energy during the recovery that they get back when the oar is in the water? It's actually pretty easy. Rowers can store potential energy using springs. On the water, it's a simple matter of attaching a spring or bungee cord to the oar handle or modifying the oar lock to have a spring return. It's a little more complicated on the ergometer. Here is how I did it. First, I 3D printed some adapters for the handle to make it easy to attach a cord. It would be easy to attach a couple of bungee cord springs to each of these to stretch back to a wall, but it would be difficult to have a fairly constant tension and adjust the tension for training or experimentation. I thought I would use gravity instead. So I attached pulleys behind the rower and then ran the cords through these pulleys up to the ceiling to other pulleys and then back down where weights can be easily added or subtracted to the cord. The ability to change weight make it easy to adjust the resistance, force, and potential energy stored each stroke. This method also makes it easy to calculate the amount of power generated during the recovery phase. As you can see, a few pounds of weight simply balances the current spring force of the handle as shown on my machine. Additional weight can be easily added as the rower adapts, or changed if a different rower with different abilities gets on the machine. The adaptation issue is not that the technique substantially changes, but the additional muscles being used have little aerobic capacity and it takes time to develop aerobic capacity. Here you can see me using the modified ergometer. A few comments. The resistance is set at 10, giving a drag factor of about 210. None of those weenie drag factors for me. You can see the weight moving up and down behind my body. The rowing action is exactly as it usually is for me. I used some pretty cheap stuff in trying this out, and I think the action would work smoother if I used higher quality pulleys and rope. What surprised me was where I felt the fatigue that started after only 3 to 4 minutes with a few pounds of resistance. I felt it in my deltoids and the shoulder, akin to repeatedly pushing things on a shelf above your head, I guess. I'm sure more elegant solutions can be devised, but at least it works. Proof of concept. You're probably asking, is this legal? My reading of the rules say yes. Shell modifications are allowed as long as they are commercially available to all. Springs should qualify. But what will it get me? 1 foot-pound per second is 1.36 watts. I move the handle about 4 feet each stroke. A 1 pound weight at 30 strokes a minute adds 1 times 4 times 30 divided by 60, or 2 foot-pounds per second work. or about 2.75 watts to the output. 10 pounds would add almost 30 watts, and 20 pounds almost 55 watts. Of course, such benefits would take a lot of time and effort to achieve because physiological adaptations occur slowly. Only you can answer whether such improvements might be worth doing something a little different from what you're used to. So, in conclusion, there are many ways to improve power. The most important, of course, is to put in the time doing the training, but there is more you can do to address the physiological aspects of rowing to optimize the muscles you have trained and are still training. These are: first, improve efficiency through improving muscle efficiencies and reducing kinetic losses. The easiest way to do this is to find your most efficient drag factor. 2. Optimize stroke rate to increase the anaerobic threshold. And 3. Increase the muscle mass used while also improving muscle balance as best one can. All three of these come down to improving your technique to minimize losses, maximize muscle mass, and increase oxygen delivery, as all three are separate parts of optimizing power. Rowing technique involves more than putting the oar in the water and pulling hard, but rowers tend to ignore the physiological areas I've talked about. My analysis suggests most rowers have room for large power increases by just optimizing drag factor and stroke rate. If rowers were also to go to the trouble of making some small modifications to the shell or ergometer, then even larger improvements can be made available to the rower with enough work and time. Getting better can occur through rowing smarter rather than pushing harder. While all this may seem complicated and overwhelming to the individual, it's actually pretty simple compared to the problem a coach of an 8 faces in trying to find the right balance of all these changes for the best performance in a shell filled with 8 rowers of different sizes and abilities. Good luck to them. Thanks for listening.